Chemistry, we're moving on to the second lesson in the chemical reactions, and this is the lesson that deals with reactions and how they're structured. So chemical equations are the centerpiece of the study of chemistry. Chemical equations are a recipe that shows how reactants combine into new substances called products. So down there on the left side of that arrow are the reactants. Those are the things that you put into the chemical reaction that you start with. Side of the products, that's what you want to get out of the chemical reaction. So you want the CH4 and the O2 to recombine to form CO2 and H2O. The one-way arrow indicates that the reaction moves from left to right. We'll get into reactions in a month or so where the arrow goes both directions, meaning that the reaction can move in both directions. Okay, so here are three ways to interpret a chemical equation. You can say that one molecule of CH4, so there's an image of a CH4 molecule, and two molecules of O2 break apart and combine to form one molecule of CO2 and two molecules of H2O. Okay, and we saw in the balancing equations that you have to have the same number of hydrogens on the left side of the arrow as on the right side, which you do. You have 4. Same number of carbons, 1 on each side. Same number of oxygen atoms, 4 on each side. Okay, so you can look at it as just simply molecules matching up. So what chemical reactions do, and you've got to keep this in mind because sometimes you'll forget it when you're working with equations, they're interested in matching up numbers of atoms or molecules. By the way, sometimes we just generically use the word particle so we don't have to say atom or molecule or ion or something else, okay? So we call them particles sometimes. So this is telling you that you need 2 molecules of oxygen for every 1 molecule of CH4. And that's going to then produce 1 molecule of CO2 and 2 molecules of H2O. But we don't really deal on the molecular level here. We can't see molecules, we can't measure them, we can't weigh them. So the other way, the next way, is we can view them in terms of moles. So moles are these big baskets of molecules that are big enough for us to actually see with our eyes and weigh on a scale. So we can say that 1 mole of CH4, so there's a big basket, that's 6.022 times 10 to the 23rd molecules of CH4 makes 1 mole. And 2 moles of O2, so again it's 2 times 6.022 times 10 to the 23rd, is going to produce 1 mole of CO2 and 2 moles of H2O. So we'd rather think of it in those terms where we have a big bundle of molecules that we can actually see and weigh. However, this wouldn't be very useful as an equation if you had to have exactly 1 mole of CH4 and exactly 2 moles of O2. What are the chances you're going to have exactly that much? Not very good. So really here, the next slide will show the way that you should really think of this. We can view the equation in terms of ratios. So there's the equation. So whatever number of moles of CH4 reacts, twice as many moles of O2 are needed. So in other words, let's say we don't have exactly 1 mole of CH4 and 2 moles of O2. Let's say we have 10 moles of CH4. Then that means we're going to need twice as many. That's what I mean by ratios. You need 2 times as many moles of O2. So if you have 10 moles of CH4, you're going to need 20 moles of CO2. Or excuse me, of O2. If you have 50 moles of CH4, you're going to need 2 times that, or 100 moles of O2. So you can use any number of moles you want. It's just saying that they have to be a 2-to-1 ratio. You have to have twice as many moles of O2 as you have of CH4. Now, what is that going to produce? Well, what you do is look at the coefficients in the equation. If you have 1 mole of CH4, you have a 1 in front of CH4. If you look over to the right, you have a 1 in front of CH2. So that means you're going to get out of this reaction 1 times whatever number of moles of CH2 of CH4 that you put in. So again, if you put in 100 moles of CH4, you're going to come out with 100 moles of CO2 because it's a 1-to-1 relationship. There's a 1 in front of both of those compounds. And you're going to get twice as much of the H2O. So let's say we're starting with 50. So we have 50 moles of CH4. That means we need twice that many, 100 moles of of O2, and what we're going to get out is 50 moles of CO2 and 100 moles of H2O. So just think of it as relationships of numbers. It doesn't have to be an exact number of moles. You can pick whatever number of moles of CH4 you want, but that's going to change all the other numbers too. Okay? So let me read that at the bottom one more time. Whatever number of moles of CH4 reacts, twice as many moles of O2 are needed. This requires a ratio of 2 moles of O2 for every 1 mole of CH4, whatever those numbers happen to be. So particulate diagrams provide a simple picture of the motion of atoms in a chemical reaction. The way that chemical compounds break apart and recombine will be covered later in this course. Particulate diagrams show a beginning and final diagram of a reaction. It might also show an intermediate state. So there you have one CH4 and two O2s, and somehow, some way, they're going to break apart, and they're going to break into individual atoms like that. Then they're going to recombine, and they're going to recombine into one CO2 and two H2O molecules. Okay, so that's what particular diagram. They're just literally a picture diagram of what's going on at the molecular level in this particular reaction. This is called a three-stage particulate diagram because you start with the reactants, you show them broken apart in the middle, and then you end up with the products over on the right. Alright, so Antoine Lavoisier, known as the father of chemistry, developed the idea of conservation of mass in the 1700s. Conservation of mass means that the mass of the reactants before a chemical reaction must equal the mass of the products after the reaction. So this means that if you bulldozed and burned Hoover High School to the ground, the mass of the rubble and the smoke, so assuming you could put a big glass dome over the school before you did that, the mass of the rubble and all the atoms and elements in the smoke would be exactly equal to the mass of the school before it was destroyed. So this means that the number of atoms of each element in the products must equal the number of atoms of each element in the reactants. That's what we learned when we learned how to balance equations. Alright, and that takes care of this brief lesson on reactions. So now you know what a reaction is. We're going to be working with these throughout the entire course.